Okay, the subject of this video is a whole house fan. Ours is going to be 7 meters diameter on the blades. There are basically three parts to design on this. You have the motor, and you have the blades, and then you have a shaft that goes through all of it and connects it together. So we're going to go take a look first at the blades. Which are here somewhere. Apparently they're not on this drawing. Okay, so moving on, as they say, we have here the part that holds it all together. Let me turn this thing a little bit. What we're looking at here is the hub and the motor. The blades go on this flange down on the bottom down here, and this is 3/4 3/16 stainless rods. There's 20 of them, and they go up to mounts that are already in the ceiling. They were cast into the spider beam when it was poured. Now this is the proof of concept drawing here. We're looking at it because the motor stator is on this drawing. It takes so long to load drawings. There's a few differences between what we produced and this pre-production kind of prototype. We've extended these bolt clips to a continuous ring. They just sort of meet together about halfway between. So that's a major change. And earlier videos show these parts, the manufactured parts. I think they're on the upstairs work table. I don't know what video number that is. There've been some minor changes. This blue thing going around here has got 5 sides on it in this drawing. It's now got 10 sides, and the 1 rod through each of the 10 things. That's made it more round on the top, and so this top edge is now underneath of this purple flange here, and the one underneath, it's also moved down to be under the flange. At the top up here, this was a pair of hubs. There's a parting line right through here on your on the screen. It's a flat plate, a weld-in hub. You buy those from people like Browning and Dodge and all that. It's got a step on it so you can put it flat against the plate, then you weld around it. And then it's got a quick detachable hub. And the advantage of the hub is it's also got some threaded holes that when you switch the bolts from holding it together to taking it apart, you screw them in those other threads, and it pops these hubs out. So it's just absolutely loose on the shaft. In the actual motor, this parting line is about 1.25 inches or 1.5 inches away, one from the other. And the stator, that's the thing with all the wires and stuff that makes the motor run, it goes between those two. And each of these top and bottom plates, in this proof of concept, the bolts around the outside held 280-degree segments, left to right, it just sort of split, of 1/4 inch mild steel. And the magnets are epoxied onto that. So it was a flat plate and then 2 more pieces to mount the magnets. When I went to buying materials, I found some sprockets 21 inches in diameter for a number 50 chain, and they had the weld-in hub up here already in it, and big enough for the shaft size that we had. So we bought 2 of those sprockets and 2 hubs to match. So that's the basic changes from what the concept model is. Oh, when these were made longer, and because the 10 sides faces these rods away from each other as they go out. We now have a really wide top connection, and it sort of triangulates the structure better for torque. There's not a terrible amount of torque on this, but there's a fair amount because it's a big blade you're trying to start up. Not much drag on it when it's running. It's an upper airfoil on the blade, so it's fairly low drag. Anything else here? Let's move on to something else. Look at the actual screen. Okay, there it is. See if we can explain what this is. Okay. When I designed this motor, I started out not knowing anything about, well, this kind of motor in particular, but I did know a little bit about some motors. Kitchen appliances, power tools like electric drills that you plug into the wall, they are controlled by copper bars around the right around the center of the shaft, and carbon brushes ride on those. And the carbon bars are connected to the coils that's on the armature. That's the part that turns in the middle. The copper windings are in the middle. There's also a set of field coils around the outside that stay still. But the idea is you have to change the polarity on certain coils from clockwise to counterclockwise as it turns. There'll be like 4 coils in play. I don't care how many you have on the motor, but 4 of them are in play. The rest of them aren't connected. So that kind of limits the power for the size of the motor. But they make plenty good torque, so they're really popular. But they run on AC or DC, and they're mechanically commutated. That's why they can run on 2 kinds of power. The other kind of motors you have to electrically change the polarity of the coils. Well, as soon as you go past a 2-pole motor, 2-pole motor won't self-start. You have to give it a little push, and then it'll run according to the voltage on it. Faster it turns, you know, the more power it makes. Okay, so what I did was I looked on the internet and found YouTube, and there's a site called Muddy Mud Man, and from his site I learned about these dual rotor axial flux motors where the magnets turn and the stator stays still. And there's a sort of an important factor. When you have a magnet and you put a piece of metal through it, it attracts it. So if it's on a shaft, it turns that shaft until the magnet is as close to that piece of metal as you can get it. And this is an advantage when you're building stepper motors, like on my CNC machine. When the power's off, it pulls all those bars, and all the bars are near magnets. Like the same number of magnets and iron stator bars. So when it's not turning, there's a huge magnetic force trying to keep it being changed from where it's sitting. It's definitely stuck. And when you overpower it and actually physically turn it, it goes lumpy, lumpy, lumpy. They call it cogging. It's trying to get either back to where it came from or to the next one once you get more than halfway. That's because stepper motors, they're called motors, but they're not really motors. They look like they're spinning at 1,500 or 2,000 RPM when a CNC's running, but they are going from one position to the next. They divide a rotation of the motor. Mine divided into 2,600 steps. They're fractional steps. There's really like 1/10 of that actual steps, but it's starting and stopping that many times. It just does it so fast you can't see that it's stopping, but it's not running continuous. It's going from one step to the next step, and they count the steps, and that determines how many revolutions of the motor, and knowing how much the machine travels per revolution on the motor, you calibrate that when you set it up. You go like 100 millimeters or 100 centimeters rather, and see what the turns were, and you just move the decimal place, and that's your correction factor. But this motor here, it's going to be electrically commutated. And this diagram, that's also, I got to give credit to the people who build Moeller, I guess they're generators. I think they make them as motors and generators. Basic layout's the same. They're trying to say that there's free energy, that this thing is self-sustaining without power input. A lot of people build them. They don't seem to explain to these people how they work or why they work. And the efficiency of them is way less than 1%. One big as a house might make 1/3 of a horsepower. But they do continue to turn. And there's a reason for this, at least as best I can figure out from what I read on them. They're working on hysteresis. When you magnetize a piece of metal with, I don't care if it's electromagnet, bar magnet, permanent magnet, whatever, it lines up the molecular structure of the metal and makes magnetic field lines, connect north to south. And as long as the power's on the electromagnet or the permanent magnet is touching it, you got a magnet. When you take away that permanent magnet or you cut off the electric on an electromagnet, the magnetism goes away over time. If you were in high school science class, you took a U-shaped bar magnet, picked a nail up with it, and you could pick other things up with that nail because it was magnetized. When you pulled it away from the magnet, the stuff didn't fall off of it for like half a second. And that's hysteresis. That's the motor's trying to remain, or the metal's trying to remain magnetized, and it just fades. So if you make enough of that, you're trying to work on the coast time when you're not powering it in, but you still have magnetism. The next thing that these Moeller motors seem to employ is inrush current. You take an electric coil and suddenly connect it to electricity, across two wires. I don't care if it's AC or DC. DC is the easiest to understand, though. There's no resistance to the electric going into that coil, except the resistance in the wire. V equals IR, that kind of resistance. But as the wire rushes around this coil, it starts making a magnetic field which bucks the current coming in. So the actual current going through it after the first fraction of a second, or maybe it's, on big electrical motors it could be 7 or 8 seconds, it drops to 1/3. Or the way we put it, it's rated to run at a certain amps, but your inrush power is almost 3 times that number of amps. So it's this terrible rush of electricity in, and compared to the resistance of the wire, and then the hysteresis of the magnetism. I'm not ever going to build one of them, but it comes up with ideas. And what I got from that site was this wheel you're looking at here with all the colored circles on it. The stuff around the outside is just for me to keep track of what's going on. The actual part is the dark, looks kind of purple on my screen. That's got red, green, and blue little circles on it. If you have a magnet that's north and a magnet that's south, they attract each other. You have to have two more north magnets, they push each other apart. So if you have this thing sitting at any position and you turn on power to the coils, the ones that want to attract, and the ones that want to repel. So the idea is that you either wind them clockwise or counterclockwise. That way when they power up, it turns the motor. And because the motor has magnets that are north side up and south side up, north polarity and south polarity, that makes it continue to turn. The next little piece is my own invention. The ones that, I got an arrow going out here to the side. Let me move this down where you can see that. Okay, what this is saying is the coil that's blanked out with the, just sort of made it all the same color as the disc, it's not connected to any wire right now. But the red and the green are. And the things in the back here are the coil, and the things on the front that you see here is the plate. That's the magnets. So the red and the blue are trying to turn that direction. The purple's not doing anything. It's just it's doing nothing. It's pointing away from the axle. And I rated these things at if they were not quite yet aligned. Like this one is trying to get centered up on this. This one's trying to get centered up. This one is starting to get near it, but it's influenced by it. As you go around this circle, you see how they start to change. And the way this was explained on this Moeller Motor site, they took the holes. Where's my thing? They took the holes and put them in one piece of cardboard, and they put them over another piece of cardboard. They had these colored circles on it. That's definitely copied from the man. I don't know the name of his site, but it was on YouTube too. And then they put a pin in the middle of the two pieces of paper. And as it turns, you can see these magnetic fields lining and unaligning. Well, from the Muddy Mudman site, I found out that to avoid cogging, you want a different number of magnetic poles and stator coils. That way, some of them are fully engaged, and some of them are coming in, and some of them are going out. But the idea is that they don't all hit at the same time, like on a stepper motor. The more you have, the less cogging you get. He seems to have like 9 and 12, or 6 and 9, either way. 6, 9, or 9, 12. The trick to it is you have 3 phases on this motor. This motor's got a green phase, a red phase, and a purple phase. All the greens come on at the same time. All the reds would come on at the same time. And if they were lit up here, all the purples come on at exactly the same time. So, because you got 3 phases, the number of coils has to divide by 3. Like 3 3s are 9, 3 4s are 12, 3 5s are 15, 3 6s are 18, 3 7s are 21. Anyway, so they divide by 3. Magnets are either north or south polarity. So you have 2 choices. The number of magnets has to divide by 2. So I put various numbers of these things. I didn't use paper. I did it in the computer where I could just turn it into groups, blocks, like I mounted them on the same axis. That's what these things out here on the side are. That's my little handle I grab with my mouse to turn this so I can watch what's happening inside the windows. This is not part of the motor. This is part of the test rig. This whole thing is the test rig. What I discovered is that they were all working to pull, in this case, clockwise, until down here. This one's already centered. So after that, they're doing less and less, and pretty soon when you get up around here, that last 90 degrees or maybe a little more, they're trying to make it turn the opposite way. They're taking away power. Instead of making more power, they're taking away power. And that's just the way motors are made. Except my motor. This is I know it works with the 27 and 30 coils versus I don't know, different ones. But what I did here is, you see it, this is clockwise, counterclockwise, clockwise, counterclockwise. And here we go, clockwise, clockwise. 2 of the same polarity side by side. What that does is it skips the second 180 degrees of rotation back to what it was on the first 180 degrees. So every one of these magnet sets is pulling when the power goes on. the entire ring is all pulling. You're not subtracting 90 degrees from 270 degrees of power and getting 180 out of the total 360. You're getting 360 degrees of power out of 360. And with this high number, it might have a cog in it when it passes these two clockwises. But the percentage of rotation at the speed it's running, I don't think it's a problem. I haven't not built the stator yet. But this is a proof of concept and how we are going to build it. We're definitely going to build it like the drawing because it looks like it works great. And it's always making power on two phases at the same time. That's another thing. The way this is done, the red and the green are both making power. There's 2/3 of your total coils on the thing are both pulling in the same direction. The other one doesn't make any difference. It's turned off. Or more correctly, it's not turned on. And then you have a that's what they call those anti-lock brake sensors. It's senses a magnet, and boy, I wish I could remember the name of that thing. Can't remember it. It's the same a little sensor that senses a magnetic field or bouts. If I could think of it, I should have wrote it down. Didn't. Anyway, it tells you the position of the rotor, and there's two of them used, and one turns the on to the next phase, and one turns it off. I'm going to use 6. I'm going to use each phase is going to have its own. They're all tunable, and if I have any problem with cogging, I'll kick one of those things like 2 degrees forward or back, and the other one the opposite way, and I'll lose a dab of power, but it'll stop the cogging altogether, because it'll buck. The cogging will buck, and it won't pull. So we have a 3-phase motor, groups of 3 coils. Now you have to control this. You have to turn this stuff on and off. And another YouTube channel, Electro Noob, he has all kinds of electronic projects with diagrams and assemblies and materials lists, and he has 3 of them on the control of 3-phase motors. It doesn't make any difference whether it's like these flat plates like this one is an axial flux. The flux goes up and down along parallel to the shaft. Most motors are built radial. The ones you put in, if you're making an electric car and you want to make a motor, you're going to use a cord motor. Instead of this one here, the coils are coils. There's no metal core in them. It's just a copper coil. If you're putting magnets and coils, the coils stay still, the magnets turn. Behind the brake rotor on your car wheel, you can make a 50 horsepower motor and put it in one each and 2 wheels and drive forever. But they use these same sensors to do that. I can't remember the name of that sensor. Oh well, that's something you can look up somewhere else. I think that's all there is to this video. This motor doesn't need any kind of electronic commutation if you use it as a generator. So we're going to make another one. It'll probably be a little smaller diameter. This one's like 21 inches across. And I think we'll make one that's about 16. Same number of magnets, same number of coils, everything the same, just scaled down. And that's going to go on a vertical axis wind turbine. Goes on the roof. And we haven't been able to get electricity from Morocco. And I quit even talking to them about a year ago now. I haven't been there. They want the house completely wired with ready to throw the switch when it connects to their Morocco lines. We're wanting electric to build the house with and to test as we do the wiring to see that things are right. But we can't get electric. We could have got a temporary pole, which you renew every 6 months. You renew the paperwork, not the pole. But once you break ground, you can't get that. and we're expats. So, well, my wife's Filipina, but she worked long enough out of the country that, you know, dual citizenship and all that. They look at us and then they look for all the paperwork that generates, you know, in the bottom drawer of their desk. And they pull out paperwork for a temporary pole for the expat. And they wanted us to have the provincial electrical engineer, a licensed electrician, and 2 electrician helpers on site for the duration of the install of our temporary pole. They had no idea how much that would cost. How you would tell the provincial engineer he has to go out into the provinces and stand out in the sun for a day and a half while they connect 2 wires up. I don't know how you'd get that guy to come, and then schedule these other basically minimum 3 people to be there. So we skipped the temporary pole. The problem was that we'd already broke ground. You should get your temporary pole before you do anything else. The water seems to be simpler, but with the problem I had electric, I've just sort of not wanted any new problem, so I haven't talked to the people. But they're privately owned where we are, so you're not dealing with the government, you're dealing with an individual company. And I have the feeling that will go much better. But we haven't done anything on it. We have a city water to the helper's house, you know, that's on the property where they live. They hooked it up themselves, so you get a bill every month. But so we had a well when it would work. Yeah, hand pump. You work it for a day after you put new parts in, and then it quit. I think the pipe has got a crack in it in one of the threads going down in the well. And we haven't pulled it up yet and looked. Anyway, we're building a generator, vertical axis wind turbine. I would have done it already. It's a simple thing. It's just this kind of a motor and some styrofoam blades coated in fiberglass. We call it surfboard technology. Our hobby is small airplanes, you know, owner-built airplanes, and we build them out of fiberglass and styrofoam and blue-on plywood and phenolic and whatever. So it's not a new technology to us. We're kind of used to the smell of it and the sanding of it. We're going to do a video on the design of the wind turbine. Probably group it with this one, which is a follow-on to one called 3- and 4-way switches and why you need a 4-way switch in your bedroom. I've been uploading on it about 22 hours so far, and it's at 11%. So I don't know how long it's going to take before if it makes it before it gets into upload terminated or upload abandoned or whatever they put up and you have to start over. But if it goes right on through, I'd expect in 2 or 3 days it'll be up. And then I'm going to put this one right behind it, and then I'll put the electric generator, the turbine, wind turbine. It's a booster turbine, airfoil blades. There's no back pressure on the advancing blades trying to slow it down. Every bit of wind that goes across it is turning it. It gets 2 shots of turning it. It's kind of a trick. Anyway, we're going to do a video on that thing too. And this, we're going to try to turn it off. And if you've learned anything about anything on here, motors, magnets, whatever, you can give us a thumbs up. If the explanation was just not clear, because I'm not professional, I'm an engineer, I'm not a lecturer, you can give us thumbs down. And in this case, you won't have to give me a comment of why it's thumbs down. I know exactly why it would be. I don't know about I subscribe to channels, but I usually have tabs open across the whole top of the computer, so I just check them every day. But if I want to remember Electro Noob and I haven't used this channel for 6 months, it's good to be subscribed to it. There's a notifications bell. I've never used it because, like I say, I check the ones I'm interested in really regularly, and I got 117 subscriptions. So when I get bored, I go through my subscription list and just pick somebody. They show you which ones have got new videos, like some Pedro and somebody. Bertie and Pedro. That's a Filipino couple building their own house. They're about as much hurry as we are. Money limited, same as us. Anyway, this group is going to have another one about electrical things, and it's going to be that wind turbine. So they sort of be grouped together. And I don't know what's after that. Anyway, y'all have a nice day, and I'm going to end this one at whatever time it is. Oh, golly, it's 30 minutes off. Bye. Have a great day.